Hello everyone, I'm just going to quickly go through two of the questions I set you on Hubble based around V equals H0 D. First of all, we needed to calculate the Hubble constant and do it in kilometres per second per megaparsec. So start with H0 equals 1 over age, and then H0 is then equal to 1 over the 13.7 times 10 to the minus 9 years, so you need to multiply that by 3.16 times 10 to the 7, which, if you look in your data sheet, are the number of seconds in 1 year. So now we've multiplied by years by the number of seconds to find out the total number of seconds to the minus 1, because we did 1 divided by that number. So 3.16 times 10 to the 7 is found in your data sheet, and that's far easier than working out how many seconds in an hour, how many hours in a day, how many days in a year. So do make sure you're aware that's available. So the next step is to work out the Hubble constant. So we use our previous value and multiply that by the number of meters in a parsec, and then we need to multiply that by 10 to the power of 6 because it's in megaparsecs, and then divide that through by 1000 or 10 to the 3 because of the kilometers, and then you end up with 71.4. Now others of you may not have followed that, so here's another alternative route to answer the same question. So we're trying to find kilometres per second per megaparsec. So let's find out what 1 kilometre per second per megaparsec is. So rewrite that, so that's kilometres per second divided by megaparsecs, so 1 times 10 to the 3, because it's 1000 metres per second, and then divide that by 10 to the 6 for mega, and then 3.09 times 10 to the 16 for megaparsec. So that then equals 3.24 times 10 to the minus 20 per second. Now earlier we calculated Hubble's constant in per seconds. So what we now need to do is work out how many kilometres per megaparsec have happened. So if we do the large number times 10 to the minus 18 divided by the small number times 10 to the minus 20, we then get 71.4, which is the correct answer. For the next bit, the wavelength of the hydrogen alpha spectral line is 656 nanometers. And then we need to calculate the observed wavelength in the spectrum of this galaxy, which is 50 megaparsecs away from Earth. So the next step is to do V equals H0 D, where H0 is our previous answer, 71.4. The distance is 50 megaparsecs away, and the next step is to then multiply this by 1000 because it needs to be in meters per second for velocity. So that comes out as 3.57 times 10 to the power of 6. Now our equation, delta lambda over lambda equals V over C, which of course equals Z as well. So that's 3.57 times 10 to the 6 is our velocity, and then the speed of light 3 times 10 to the power of 8. So that comes out from a calculator to be 1.19 times 10 to the minus 2, and that's our value for Z. So if we rearrange the equation, delta lambda equals lambda multiplied by Z, or V over C, that then equals our 1.19 times 10 to the minus 2 multiplied by our laboratory value of 656, and that then equals 7.8 nanometers. Now because in the question it says that it's away from the Earth, we have to add, the wavelengths are getting longer, it's red shifting, so 7.8 plus the 656 gives us an answer of 664 nanometers. So for the next bit, I've put in the mark scheme so that you can read it through yourself, but you needed to mention the idea that the universe started hot or was infinitely dense, and then as the universe expanded it has got colder or cooler, and then we currently measure the temperature of the universe on average at about 3 Kelvin or 2.7 Kelvin, and then that temperature is then linked, because we see it as a black body, that temperature is linked to microwaves or microwave background radiation. Or you could have then mentioned the idea that when the universe started, when it was infinitely hot and dense, it started as gamma rays, so high energy rays, that then over time, as it's expanded, have stretched into microwaves. And then finally on this bit, I asked you not to do that question because we haven't yet covered it in the course. So for this question, we have a galaxy of 1.4 times 10 to the 25 receding from Earth at 3.4 times 10 to the 7, and we have to calculate H0. So we know V equals H0 D. So V is 3.4 times 10 to the 7, and that's then equal to H0 multiplied by the distance, which is 1.4 times 10 to the 25. So rearrange for H0. So V over D, 3.4 times 10 to the 7 over 1.4 times 10 to the 25, and that then gives us an answer of 2.4 times 10 to the minus 18 per second. Some students decided to give an answer in kilometres per second per megaparsec, which is fine, and then the answer for that you will have got is 75. But if I were you, I'd try and keep things as simple as possible, especially as it's not explicitly asking for any unit, so keep it simple with just per second. Moving on to the next one, the age in years of the universe. We know age is 1 over h0, so that's 1 over our previous answer of 2.4 times 10 to the minus 18. So the age in seconds comes out to be 4.17 times 10 to the 17 seconds. So we know 1 year is 3.2 times 10 to the 7 seconds. So it's a case of finding out how many years. So we divide the big number by the small number, 4.17 times 10 to the 17 divided by 3.2 times 10 to the 7. And then we get the number of years as 1.3 times 10 to the 10. For question 2, the maximum distance in parsecs we observe from Earth. So we know that the distance is velocity times time, and we know the velocity is 3 times 10 to the 8, speed of light, and we know the time taken is 4.17 times 10 to the 17. So the total distance since the beginning is 1.25 times 10 to the 26 metres, but we're asked to find it in parsecs. So to do that, we do 1.25 times 10 to the 26 and divide that through by the number of metres in 1 parsec, 3.1 times 10 to the 16 metres. And then our final answer, 4 times 10 to the power of 9 parsecs.